Hello everyone, I hope that you all are doing well. Today we discuss about the monotone convergence theorem and its nice application. Okay, before that I will assume that you all are well acquainted with some basic results of real analysis and some basic results of the measure theory. Means what is the meaning of measure space, measurable set and sigma algebra. You should know all of these things. Okay, then we can discuss this topic in a nice way. Here this triplet omega, sigma and mu is called the measure space. Here omega is a space. For example, it can be 0 to infinity or the standard real number set R. Okay, and sigma is nothing but the is called the sigma algebra. It contains set of all measurable sets, and mu is the standard measure. For example, you can take it as a Lebesgue measure. Okay, and x here x is a subset of omega, and it lies in this sigma algebra. Means x is a measurable set, and we consider fk greater than equal to 1 be a sequence of non-negative measurable functions on the set x. Means all these functions are defined on the set x, and it's this family should have this monotonic property. Then we can infer that the supremum of these functions is a measurable set, is a measurable function, and the main result is that this integral limit exists. Means we can pass the limit inside the integral by using the monotone convergence theorem. Okay, and this monotone convergence theorem has a very simple and nice application. Let us look at this. Let us look at the application. Okay, and this application is simple one. Means it says that if f lies in this L1 space, I hope that you all are well acquainted with the L1 space. It is the Lebesgue space. Means it is a Lebesgue space, and in particular it is a Banach space. Banach space means it is a complete nonlinear space, and it contains all the measurable functions such that this integral limit 0 to infinity modulus of f of x dx should be finite. It contains all the measurable functions which satisfy these conditions. Okay, then it is a Banach space with respect to this norm. If in the particular case if we consider this norm as L1, then with respect to this norm it is a Banach space. What this result is saying? It is saying that if a function lie in this Banach space, then the tail of this integral should goes to 0. Means if a function is integrable, then the tail of the integral should goes to 0. It is a very nice application of the monotone convergence theorem. But before going to show this limit, first we will by using monotone convergence theorem we will show that limit r tends to infinity integral from 0 to r fx dx. This limit will converges to what? When r goes to infinity, from the intuitive logic, it is easy to realize that it should goes to 0 to infinity f of x dx. But we will provide a mathematical proof by using the monotone convergence theorem. First we will show this one. To say this one, first we have to show that this limit should exist. First we will show the existence of the limit, then we will show that this limit converges to this one by using the monotone convergence theorem. Let us proceed to show that this limit should exist. Means this limit r tends to infinity 0 to r fx dx, this limit should exist. Okay, first we will show this one. Okay, let us proceed to show this limit, existence of this limit. Since given that our function is a non-negative function, our function is given that f is non-negative, so it satisfies this inequality. Means these ri's are increasing one. So when r1 is less than equal to r2, then the integral from 0 to r1 should be less than equal to integral from 0 to r2, because f is a non-negative function, so it satisfies this monotonic property. So it implies that our family is a monotonically increasing family, and it is also bounded above by what? It is also bounded above by 0 to infinity f of x dx. Means this all these functions, this one, and this one, all these are bounded by what? 0 to infinity f of x dx, because our f is a non-negative functions, and this is finite because this is bounded by 0 to infinity f of x dx, f of x modulus dx, but this is nothing but the modulus, because our f is a non-negative function. If we consider also modulus, then there is also no problem, and this is finite because f lie in the L1 space, and from the definition of the L1 space, this integral is finite, and all these these integrals are bounded by this one. So our family is a monotonically increasing family and bounded above by this. Therefore, from the standard real analysis result, it says that if a family is monotonically increasing and bounded above, this limit should exist. Okay, so right now we proved the existence of the limit. Then we will show that this limit converges to this one. Our next target is to show that when r goes to infinity, the integral from 0 to r f of x dx converges to the integral 0 to infinity f of x dx. And this is the right place to apply the monotone convergence theorem. To apply the monotone convergence theorem, we consider a sequence of positive real numbers Ri. Means our technique is to show that we have proved that this continuous limit exists. We know that if a continuous limit exists, then the sequential limit also exists, and they converges to the same limit. Okay, and our technique is to is that we will show that the sequential limit converges to this function 0 to infinity. Then we conclude that the continuous limit also converges to the same limit from the uniqueness of the limit. Okay, so we will consider a sequence Ri, sequence of Ri's, and these are strictly increasing functions and increasing numbers, and they converges to the infinity. Okay, by using this sequence, we will define the functions f(ix), and f(ix) is the nothing but the indicator functions multiplied with the f of x. And from the definition of the indicator function, means one type of characteristics function, indicator or characteristics, indicator. Okay, indicator functions, it gives value 1 when x belongs to 0 to Ri, and it gives value 0 when outside of the set. Okay, so if we open this definition, we will reach to this one. If fi's are defined in this way, then clearly it will satisfy this monotonic property. And then by using the monotone convergence theorem, say that the supremum of this fi, if f is equal to the supremum of fi, then f is a measurable function, and it satisfies this integral inequality. Okay, but here it is not Ri, it is called I goes to infinity, limit I goes to infinity. But when I goes to infinity, okay, I goes to infinity, it gives 0 to Ri and this one. But when I goes to infinity, Ri goes to what? Ri goes to infinity. This limit also can be converted to limit Ri tends to infinity 0 to Ri f of x dx is equal to integral from 0 to infinity f of x dx. And this is the application of the monotone convergence theorem. And we showed that the sequential limit converges to this one, but we have already proved that the continuous limit exists, so the sequential limit also approaches to the same limit. Okay, so therefore we have proved this result. And now our next target is to show that our required result, the tail of the integral should goes to 0 by using this one. So we consider the tail of the integral, it is r to infinity f of x dx, and this is nothing but the 0 to infinity f of x dx minus 0 to r f of x dx. Then we will take the limit on both sides, but we cannot directly take the limit on both sides, because in the right hand side we know that this function, when r goes to infinity, the limit of this function is well defined. It means it exists and it goes to the 0 to infinity. But in the left hand side we have not proved that whether this limit exists or not. Okay. Also, when this left hand side is equal to the right hand side, if the right hand side limit exists, left hand side also limit exists, then you can take also. But for the safe side we are taking the limit supremum, because limit supremum can be taken at every point. Okay. We have taken the limit supremum on both sides, but we know that limit supremum converges to the limit. If the limit of a function exists, then the limit supremum and limit infimum both are same and they converges to the limit of the function. So it converges to the 0 to infinity here, or in the right hand side we will get 0. So in the left hand side we are getting the limit supremum, but we know that limit supremum is greater than equal to limit infimum, and our function is non-negative. So our limit infimum is greater than equal to 0, and it is also bounded by 0 by the limit supremum function, but limit supremum function is equal to 0. Therefore limit infimum is also 0. Means we have proved that limit infimum of r to infinity f of x dx is also 0. From a and b we concluded that the limit of r tends to infinity, f of r tends to infinity, integral from r to infinity f of x dx is equal to 0. Means we have proved our required result, that if f belongs to L1 and non-negative, L1 0 to infinity and non-negative, then and non-negative, then this limit should goes to 0. Means the tail of the integrable function is always equal to, always converges to the 0. Okay. I hope that you all understood it very well. Thank you everyone.